The main panel is the heart of every electrical installation. In this video, we're going to walk through all the major components inside a main electrical panel, look at where we get different voltages from, and answer the burning question, why do we sometimes land the neutral and the ground on the same bus bar? Hey, my name is Dustin. I'm a licensed master electrician. Welcome to this episode of Smarter Sparky. These are the service entrance conductors, and in order to understand where they go in the panel, we need to understand where they come from. So let's zoom out and take a look at the big picture. This represents the utility transformer. It could be mounted up in the air, or it could be mounted on the ground in a pad-mounted configuration. Here I've got it as if it was mounted up on a pole. This wire going overhead from the utility transformer to your house would be called the service drop. If this wire were underground from a pad-mounted transformer, it would be called a service lateral. Service drop is an overhead wire, service lateral is an underground wire. Otherwise, they do the same thing. So from our utility transformer overhead to our service, this is called the service drop. Once it reaches the mast poking up out of the soffit at your house, it goes down through the soffit and it goes into your meter socket. Then out of the meter socket, it goes directly into our main electrical panel. Two quick notes. Starting in the 2020 NEC, an emergency disconnect is now required between your meter socket and your main electrical panel, and that needs to be located outdoors for emergency personnel to shut power off to your main panel externally to the house. Now, I'm not showing that here. My installation goes directly from the meter socket to the main electrical panel, and this is what most older homes are going to be wired like. Newer homes, again, starting from the 2020 code cycle, are going to be required to have that emergency disconnect installed between the meter socket and the main panel in this wire right here. The second thing I want to address real quick is, because this is a demonstration, I'm having to use the materials I have on hand. So because of that, I'm using NM cable as my service entrance conductor stand-in. It is actually illegal to use Romex or NM cable as your service entrance conductors. It's not rated for it. So we're gonna need to pretend that this stuff right here is SER wire, which would look something like this right here. Additionally, this overhead wire would actually be this stuff right here, triplex wire. We're gonna have to use these stand-ends and we're gonna have to use our imagination a little bit. So our service entrance conductors enter from either the meter socket or that emergency disconnect that you would have on a newer home, and they enter the panel. The two hot conductors land directly on the main circuit breaker, and the neutral lands on the neutral bar. Now, notice there is what appears to be a ground wire here. Now, this is not a ground wire in the conventional sense. We're gonna actually talk about this ground wire when we talk about the grounding and bonding section coming up. So for right now, let's just disregard this ground wire heading towards the meter socket. For right now, let's just focus on, we've got two hot conductors and a neutral, and they land on their specific locations in the panel. These two hot conductors are called line 1 and line 2. Sometimes they're also called phases, phase A and phase B, or the black and the red phase. But don't let this confuse you. This is not a two-phase system. This is a split phase system. Each line is essentially half of a phase. We'll actually cover this more on a dedicated split phase video in the future. I have temporarily energized this panel so we can take a look at a couple voltage readings. If we take a voltage measurement from the black phase, line 1, to the red phase, line 2, notice we get approximately 240 volts. And if we take a voltage measurement from neutral to line 1, we get approximately 120 volts. And if we take a voltage measurement from neutral to line 2, we get approximately 120 volts. So if we want 240 volts for an appliance, we need to connect from line 1 to line 2, and we get 240 volts. But if we only want 120 volts for lights or receptacles, we need to go from neutral to one of our phases. It doesn't matter which one, but we're gonna get 120 volts. As previously mentioned, the service conductor hots or lines land directly on the main circuit breaker. This is the service disconnect, and it actually shuts off power to all downstream or load side circuits, which in this case is going to be the bus bar. But turning this breaker off does not de-energize the incoming lugs. So when energized, again, we have 240 volts coming into the breaker, and down here where it leaves the breaker, we've also got 240 volts. If we shut the main circuit breaker off, The output from the circuit breaker is 0 volts, but the circuit breaker is off. We still have 240 volts coming in to the circuit breaker. So shutting this circuit breaker off does not turn off everything in this panel. These two lugs right here are still energized. Turning this breaker off only shuts off these bus bars underneath. So what that means is touching these two lugs could result in shock or electrocution. Furthermore, if you were to drop a screwdriver, a wrench, or a screw across those lugs, or from those lugs to the panel, or from those lugs to the neutral bar, that could result in an arc flash or an arc blast. So the main circuit breaker only interrupts the lines or the hot conductors. The neutral always remains connected. So the switch side of the main circuit breaker actually feeds these bus bars, which is where we're going to connect our circuit breakers. These bus bars are insulated from the case with this plastic carrier, so they do not make contact with the case. Each one of these exposed locations is a spot for a circuit breaker. Now, each exposed spot can actually feed a breaker on either side. So this would be the location for breaker number 1. This would be the location for breaker number 2, breaker number 3, 4, 5, 6, etc. All the odd number breakers go on the left side, all the even number breakers go on the right side. The hot bus bars are arranged in an alternating row pattern. That means is the first row of breakers is going to be connected to line 1, the next row of breakers is going to be connected to line 2, then the third row of breakers is connected back to line 1, then the fourth to line 2, etc. So they alternate back and forth as to which line they are connected to. So based on those rules, circuit 1 and 2 are always connected to line 1, circuit 3 and 4 are always connected to line 2, etc. So if I take a voltage measurement between two rows, I get approximately 240 volts. If I take a measurement from one row to neutral, I get 120 volts. And if I take a voltage measurement to the next row, I also get 120 volts. Again, if we go back from row to row, we get 240 volts. Now, if I was to skip a row, I'm going to get 0 volts because now I'm taking the same measurement off of the same lug, just like this, 0 volts. Because remember, every other row is connected to the same line. This style panel does a great job of physically covering up the bus bars. But this panel has exposed bus bars, making it even more dangerous to work in when live. In this panel, breakers are installed by snapping one side of the breaker into this plastic support bar, and the other side pivots and snaps onto the bus bar. Heavier duty panels might use bolt-in breakers, but the concept is the same. The breaker makes contact with the bus bar to get power. Here I've installed a circuit breaker in a random position in this panel. It is going to connect to one of the bus bars, either line 1 or line 2. In this case, because we are in the third row, we're going to be connected to line 1. And one side of our circuit is going to be fed from this circuit breaker, and the other side of our circuit, our return path, is going to go to neutral. And when we do that, we get 120 volts for that load. If we install another circuit breaker right underneath it, and we measure voltage from that breaker to neutral, we also get 124 volts. Again, because now this second breaker is connected to a single bus bar, which then in this case connects to line 2, which from line 2 to neutral, we get 120 volts. So it doesn't matter which line we are connected to. If we are referencing one of the hot conductors, one of the lines, and neutral, we're going to get 120 volts. Any line to neutral circuit will provide 120 volts. But what if we need a 240 volt circuit? That's where a 2-pole breaker comes into play. These things work in a very similar fashion to single pole breakers. They will snap onto this plastic support rail here, and then in this case, it's going to tap off of 2 of those bus bars. And because this 2-pole breaker connects to those alternating bus bars, we're going to have 240 volts available on the output of this breaker. So if we take a voltage measurement from both of the terminals on this 2-pole breaker, there's our 240 volts. So we can source 240 volts for whatever branch circuit we need from these two lugs right here. Now that being said, there are some 240 volt appliances that include a neutral with their branch circuit, but that's only so that appliance can reference that neutral internally from neutral to line to get 120 volts for their internal controls. That way the manufacturer doesn't have to include an internal step-down transformer. So what if we didn't have a 2-pole breaker? Could we install 2 single-pole breakers right next to each other and get 240 volts this way? Well, if we put them next to each other and take a voltage measurement, yeah, we get 240 volts. Because again, we're tapping off of just those 2 lines. But this isn't safe, because if one line were to trip, the other line may not trip, especially in those loads that might also include a neutral. For loads that tap off of multiple lines within an electrical panel, both lines have to trip at the same time. So you're probably saying, well, Dustin, could we just install a piece of wire between the 2 circuit breakers, right? Could we just do this? Because these circuit breakers have holes in them, right? So now both of these trip mechanisms are connected together, right? Well, let's test that. If I flip this bottom one on, why isn't it going on? That's because this wire is so flexible, it's not able to turn this top one on completely. Now, if I force them both into the on position, sure, they stay. But what if this bottom one trips? Okay, in this case, it tripped the top one, but that just might have been coincidence. What if this wire bends just enough that it does not trip that top one? Again, we can't reset it by trying to flip one or the other. There's just too much flex in that wire. Well, what about using a thicker wire? Sure, you could give it a try, but here's the problem. There is no way for you to guarantee that whatever you put between those 2 breakers is going to ensure that those 2 breakers trip together. That's why it is not okay to use 2 single-pole breakers in order to get 240 volts. Will it work? Sure, you get 240 volts. Is it safe? Absolutely not. Don't do this. This I see out in the field all the time. It is not safe. Do not do this. Make sure to check out all the other videos on my channel, past, present, and future, for specific branch circuit installations. This video right now is just focused on the main electrical panel. We'll install a 240 volt branch circuit in another video. Now let's talk about neutral and ground. The neutral bar is easy to understand. For a 120 volt circuit, current leaves on the hot conductor and returns on the neutral conductor. Simple as that. But why do grounds land on the neutral bar sometimes? In order to understand that, we need to know the purpose of the ground wire. It's there for safety and does not carry current under normal conditions. If a fault occurs and the hot touches a metal component, the ground is going to act as a return path for that current to flow, so we trip the breaker and shut that fault off. So the breaker trips and clears that fault. In order for that to work, ground and neutral are required to be connected together in the main panel. The point at which this happens is called the main bonding jumper. And in most residential panels, it's this green screw bonding the neutral bar to the metal enclosure. Because grounds and neutrals are required to be connected together anyway, they're allowed to terminate on the same point in the panel. The ground rods are simply a reference to Earth. They have nothing to do with tripping a breaker. The only time they carry current is during a lightning strike or a large surge. Earlier we saw a ground wire entering with the service conductors. This is actually called a supply side bonding jumper. And that bonding jumper extends the ground connection back to the meter socket or emergency disconnect. Grounding and bonding is a complex subject and is actually the largest article in the NEC, so we could spend hours talking about this. This is just a high-level overview to understand what's happening inside the main panel. In a dedicated grounding and bonding video, we'll cover why neutrals and grounds cannot be connected in subpanels, how separate ground bars are handled in main panels, and how water pipes, rebar, and other grounding electrodes factor into the system as well. So let's zoom back out and take a look at the big picture. Power comes from the utility transformer through our meter and into our main electrical panel on the service entrance conductors. The main breaker serves as the service disconnect. It controls the flow of power to the hot bus bars, which feed the individual branch circuit breakers. Single pole breakers connect to one of the hot bus bars and supply 120 volts. Two pole breakers connect to both hot bus bars and supply 240 volts. For 120 volt circuits, the return path is the neutral, and for 240 volt circuits, the current flows out on one hot and back to the other hot. The neutral is not part of the current path. Now again, some 240 volt appliances include a neutral, but that's only so they can run internal controls off of 120 volts. The equipment grounding conductor is not part of normal current flow. They are there strictly for safety, providing a low resistance return path in the event of a fault. In the main panel, the neutral and ground are bonded together through the main bonding jumper. In sub-panels, they have to remain isolated. And the ground rods are not there to trip a breaker. They are only a voltage reference. The only time they do anything is in the event of a lightning strike or a surge. Hopefully this video has made what's inside of a main electrical panel less random and more logical. In future videos, we'll dive deeper into topics such as how split phase actually works, grounding and bonding in more detail, and specific branch circuit applications. If you made it this far, don't forget to like and leave a comment, and consider subscribing if I've earned it. There is a Patreon link in the description if you would like to support the channel further. Thanks for watching. We'll see you on the next one. Bye.